Welcome back. In this video, we are going to solve exercises 5 to 7 of chapter 5. We have two metric spaces, x dx and y dy, with y complete and a subset A of x. We have to show that if f is a uniformly continuous function from a to y, then f can be uniquely extended to a uniformly continuous function g on the closure of A. Okay. This is how we construct G. We pick a point x in A bar and we will define G of x. If x is in A bar, then by proposition 1.8, there exists a sequence xn of A that converges to x. So let epsilon be given, positive. Uniform continuity of f on A means that there exists a positive number delta, such that the distance between f of x and f of y is less than epsilon whenever the distance between x and y is less than delta. Okay, so the delta depends only on epsilon and not on x. Now, since xn converges to x, then the distance between, so in particular xn is a Cauchy sequence, so the distance between xn and xm can be made less than delta for all n and m large enough. But then the distance between the images is less than epsilon for all n and m large enough. So this means that f of xn is a Cauchy sequence in y. Since y is complete, f of xn has a limit y. And I take this y to be the image of x under G. Okay, but now there is, we have to check some points. First of all, we have to check that G is well defined. Why? Because the way we define G depended on a sequence xn converging to x. What if someone takes another sequence yn converging to x? Would f of yn converge to the same limit y? We have to check that. Second point, you have to check that G is uniformly continuous, and then you have to check that G extends f, which means that G of x equal to f of x for x in A. Okay, so let us tackle these points in turn. Let yn be a sequence of A that converges to x. Then, by the triangle inequality, the distance between xn and yn will be less than delta, this is an error, less than delta for all n large enough. Okay, as you may check. Therefore, the distance between their images under f will be less than epsilon for all n large enough. And once again, if we apply the triangle inequality, since f of xn converges to y, and f of xn and f of yn are asymptotic, so the distance between them converges to 0, this means that f of yn also converges to the same limit y. Okay, you should easily check that. Therefore, y depends only on x and not on the choice of the sequence converging to x. So G is well defined. Next point, uniform continuity of G. So let epsilon positive be given and let delta be as in the definition of uniform continuity of f. Now, if x and y satisfy dxy less than delta over 3, and xn and yn are two sequences of A converging to x and y respectively, then the distance between xn and x can be made less than delta over 3, and same thing for the distance between y and y. Therefore, by the triangle inequality, the distance between xn and yn will be less than delta, as you may check. Therefore, by uniform continuity of f, the distance between f of xn and f of yn will be less than epsilon for all n large enough. Now, by definition, f of xn converges to g of x, and f of yn converges to g of y. And therefore, if in this inequality I let n tend to infinity, using the continuity of the distance, I get at the limit, the distance between gx and gy will be less than or equal to epsilon. And this proves uniform continuity of G, but with a different delta. So in uniform continuity of f, we had delta, but in the uniform continuity of G, we had delta over 3. Okay. Now last point, why G extends F? Because if X is an A, then we just can take the constant sequence Xn equal X. Then G of X by definition is the limit of f of Xn, which is the limit of f of X, which is f of X. And that's it. So we extended F to the closure of A in a uniformly continuous way. Okay. So in particular, if A is dense in X, then we can extend F to the whole space, okay, by density and uniform continuity. This is a very useful result. Okay, so this concludes exercise 5. Exercise 6. We have two distances d and d prime on the same set X that are Lipschitz equivalent. Okay? We shall review what does this mean. You have to show that xd is complete if and only if xd prime is complete. Here we have to assume something stronger than just topological equivalence. Okay? Because if we have two topologically equivalent distances on the same set X, completeness of X with respect to one of them does not imply necessarily completeness with respect to the other. So here we are assuming something stronger than topological equivalence. Okay, what does Lipschitz equivalence mean? It means that the prime of xy is bounded by alpha dxy and beta dxy for some two positive constant alpha and beta. Okay? This is the Lipschitz condition. So in particular, d and d prime are topologically equivalent, but the converse is not true, as we know. Okay, now suppose that xd prime is complete. We have to prove that xd is complete. How do you prove that? In the usual way. We pick an arbitrary Cauchy sequence xn in xd. Okay? And we write the Cauchy condition. So given epsilon positive, the distance between any two terms of the sequence in xd is less than epsilon. Okay, therefore, this d is less than epsilon. So beta d xn xm is less than beta epsilon, and therefore d prime of xn xm is less than beta epsilon for all n large enough. This inequality means actually that xn is a Cauchy sequence for d prime, because if epsilon was arbitrary, then beta epsilon is arbitrary. If you wanted to have epsilon exactly here, then you would have taken, you should have taken, instead of epsilon here, epsilon over beta. Okay? That's the same thing. So don't worry if you don't get exactly epsilon, same thing. Now, so xn is a Cauchy sequence in xd prime, and since xd prime is complete, then xn converges to some x in xd prime. So this means that the distance d prime between xn and x tends to 0 in the usual sense, in the usual distance of R. Now, if you look at this inequality, dxnx less than 1 over alpha d prime, but d is positive. So what do we have? dxnx is between 0 and 1 over alpha d prime xnx. So by the sandwich theorem, dxnx converges to 0, and therefore this means that xn converges to x in xd. So we started with an arbitrary Cauchy sequence in xd, and we proved that it's converged using the completeness of xd prime. Now, and this proves that xd is complete. Now, since d and d prime play the same role, symmetry implies that the converse is true as well. Okay? So if xd is complete, then xd prime is complete. So this concludes exercise 6. Exercise 7, the last one. We have a metric space xd. We have to show that xd is complete if and only if for every nested sequence, okay, and of closed subsets, non-empty subsets. Nested or decreasing, same thing. Okay? So for every nested sequence of non-empty closed subsets of x whose diameter tends to 0, the intersection, the whole intersection, is a singleton. Okay? Now this is not always true. Okay? It's possible that the intersection is empty. You may give counterexamples. But here we have the assumption that xd is complete. So we have to prove two things actually. If xd is complete, then the whole intersection is a singleton, and conversely. Okay? So suppose first that xd is complete, and let an be a sequence in the statement. So decreasing sequence of non-empty closed subsets whose diameter tends to 0. Now, since each of these sets is not empty, we can choose an element xn in each an. So we have now a sequence of the space. We claim first that xn is a Cauchy sequence. This is actually a consequence of the fact that the diameter of an tends to 0. Okay. So for any p, for any integer p, xn plus p belongs by definition to an plus p. But since the sequence is decreasing, then an plus p is contained in an. Okay. So, but xn is an an. Okay. So the distance between xn and xn plus p is by definition less or equal than the diameter of an, which is the supremum of the xy in an. So the distance between xn and xn plus p tends to 0 as n tends to infinity. And this precisely means that xn is a Cauchy sequence. Now, completeness of x implies that xn has a limit x. And now we claim that x belongs to the intersection. Okay. Pick an integer m and let n be an integer bigger or equal than m. Then xn belongs to an. But since the sequence is decreasing, an is contained in an. So xn is an an. Okay, now if we fix m and let n tend to infinity, xn converges to x. So the limit must be in the closure of am. But am is closed. Therefore, x is in am. But m was arbitrary. So x belongs to all am. Therefore, x belongs to the intersection. And now we prove the reverse inclusion. So the intersection is precisely equal to the singleton x. Okay, we know that x is contained in the intersection. We have to prove the reverse. So if y is in the intersection, then both x and y are in an for every n. So the distance between them is less or equal than the diameter of an, which tends to 0. Therefore, the distance between x and y is 0, and therefore x equal y. And this proves the claim and proves the first implication. So if x is complete, the intersection is a singleton, is a one-point set. Now, conversely, suppose that for any decreasing sequence of closed non-empty subsets of x whose diameter tends to 0, the whole intersection is a singleton. We have to prove that x is complete. So we start with an arbitrary Cauchy sequence, xn, and now we have to go back to section 1.4. If we let capital An to be the closure of this tail of the sequence, xn, xn plus 1, xn plus 2, and so on, then An is a decreasing sequence of closed non-empty subsets of x. And the fact that xn is a Cauchy sequence implies, as you may check, that the diameter of An tends to 0. Okay, it's easy. You should check that. So our assumption implies that the whole intersection is a singleton x, and in particular not empty. However, according to proposition 1.2, the whole intersection of An is what we call the set of accumulation points of xn, which is in the metric case means that it's the set of all limits of subsequences. Okay, so this means that xn has an accumulation point, but since xn is a Cauchy sequence, so we have a Cauchy sequence which possesses a conversion subsequence. Therefore, the whole sequence converges to x. Okay, and that's it. So we started with an arbitrary Cauchy sequence in xn, and we proved that it is conversion. And this means that the whole space xd is complete. Okay, so this concludes exercise 7 and the exercise of chapter 5 and the whole course. Thank you for having attended watched all these videos, and goodbye.